Welcome. This is a review of Hubble's law and look back time, some of the concepts covered in labs number 11 and 12. Part 1, determining a universe's size from its expansion rate and a given time. To start, let's look at a more commonplace scenario. Question 1, if each car were allowed to travel for 1 hour, how far away would they end up? Car A travels at 25 miles per hour, Car B travels at 50 miles per hour, Car C travels at 75 miles per hour. To determine the answer, we just have to take the amount of time and multiply it by the car's speeds. So we get 25 miles, 50 miles, and 75 miles. What if we replace these cars with the universes that are expanding at different rates? Question 2. If each universe were allowed to expand for the same amount of time, how large would they end up? Instead of distance, we are measuring the volume, but we can use the same logic as we used before. Universe A, whose Hubble constant is 50 kilometers per second per megaparsec, would be the smallest of these three. Universe B, whose Hubble constant is pretty similar to our own universe's Hubble constant, would be the medium-sized universe, and universe C, which expands the quickest, would end up with the largest size. So what does this mean? We can equate the expansion rate of each of these universes to the slope of the lines on this Hubble plot. The slowest expanding universe has the flattest slope, the fastest expanding universe has the steepest slope, and then universe B is in the middle. The steeper the line, the faster the expansion rate. Since all universes are expanding for the same amount of time, the one that expands fastest reaches the largest size. That was one way that we could evaluate a Hubble plot. The second way is to use it to determine a universe's age from its expansion rate and a given size. Question 3. How much time would each car need to travel 100 miles? Car A, B, and C each have the same speed that they had in the first example. So to determine the amount of time it would take to complete this 100-mile trip, I can take the distance, which is 100 miles, and divide it by each of the individual speeds. I get 4 hours for car A, 2 hours for car B, and 1.33 hours for car C. What if we replace those cars with universes? Question 4. How much time would each universe need to expand to a size of 3.6 times 10 to the 80 cubic meters? That's approximately the volume of our own universe. Universe A, which has the slowest expansion rate, would need more time than any of the others. Universe B's expansion rate, being 70 kilometers per second per megaparsecs, gives us an answer that's pretty close to what we measured in lab number 11. And Universe C, one that expands at a greater rate, would be able to reach the same size that our universe currently has in only 11 billion years instead of 14 billion years. What does this mean? The steeper the line, the faster the expansion rate. That is true for both scenarios. However, since we are assuming that all universes eventually reach the same volume, the one that expands the fastest is going to need the least time to get to that point. Part 3 combines some of the activity we did in lab 11 with the activity that we did in lab 12. So first, as a refresher, lab 11 involved a scenario where we imagined 6 friends who all take a picture on their 18th birthday and immediately send it to the Milky Way, but they live different distances from our solar system, so it takes different amounts of time for their pictures to reach us. The distances from that activity are reproduced here, and the time that it takes for the image to reach us would just be the distance in light years multiplied by the speed of light. We can take that in the form of a ratio. If that's 1, then for example, Avery's image would reach us after 4.4 years because it's traveling a distance of 4.4 light years. We can combine some of the logic from our expansion lab with lab 11 and superimpose that over a Hubble plot. This Hubble plot is the same as the one that we saw that represented our universe, and it had different steepness at different positions. So while it's not realistic to identify or to assume that there are any galaxies that are as close as even 81 light years away, we can use the same pattern that we investigated in Lab 11 to understand how Lab 12 works. Let's say that the Milky Way is here at the origin, and we've got our two extreme cases. Avery, being only 4.4 light years away, is only 4.4 years older by the time their photo is received. So instead of 18 years old, they're 22.4 years old. Their photo shows a minimally outdated view of the universe from a time when the universe was barely younger than it is now. So Avery's photo doesn't reach us instantaneously. The light from Avery's signal can't speed up to account for the fact that the universe is expanding. Instead, it just ends up showing up 4.4 years late. On the opposite end, we have Blake. Blake is 18 in his photo, but is 99 by the time the photo is received. That's because Blake is 81 light years away, so Blake's photo is going to show a highly outdated view of the universe, and it's going to be significantly younger than the universe right now. Paying attention to the steepness or the slope of the graph instead of simply the distances, which is what we were looking at in our previous example, we can see that the slope of our Hubble plot is steep at short distances. So that means that Avery's photo was sent during a time when the Hubble plot's slope was very steep. We know that we can correlate steepness to expansion rates. So that means that the universe was expanding at a fast rate at that point in time. And we determined from our previous example that the universe we see in Avery's photo is only barely younger than the universe is now. On the other hand, the universe that we see in Blake's photo is very outdated. We can see here that that correlates with a time on the Hubble plot when the slope was fairly flat. So if a flat slope correlates to a slow expansion rate, and I know that the universe in Blake's image is going to be very, very outdated, that means that the expansion rate in the very distant past was slower than it is now. What does this mean? The following two statements are true for any Hubble plot. A universe's expansion rate is determined by the steepness of its slope. The recent past is always depicted on the left side of a Hubble plot, and the distant past is always depicted on the right side. Now, the following three statements pertain to the individual examples. If a Hubble plot's steepness doesn't change, the universe it describes is expanding at a constant rate. That's the case for the blue, green, and red universes that are on the left-hand side. There's no curvature to be found, so each one of those expansion rates is constant, just as the speeds of our three cars were. We had 25 miles per hour for the speed of the red car, we had 50 miles per hour for the speed of the green car, and we had 75 miles per hour for the speed of the blue car. Let's move on to the second plot. If the plot's slope is flat at small distances but steep at larger ones, the universe it describes is expanding at a decreasing rate. So Flat at small distances also means flat in the recent past. Steep at great distances also means steep in the very distant past. So you're going from an expansion rate that is fast to one that is slow. So that explains why that universe would expand at a decreasing rate. Finally, universe number 3 is the one that resembles what our actual Hubble plot in our universe looks like. If the plot slope is flat at large distances, but steep at smaller ones, the universe it describes is expanding at an increasing rate. For watching this, please look out for a review practice quiz that goes along with this.